Let's talk about removing those outliers and what's the best way to do that. So in the diamonds data set, we found that if we have the outliers, we can just, one option is to just filter them out. That's not the best option because you're removing the entire row of data. If you have low quality data, by the time you've applied this approach to every variable, you might find that you don't have much data left. A better approach is to replace those outliers with NA. So here's the code to do just that. And if we run it, we've removed the outliers. And then, like R, ggplot2 subscribes to the philosophy that missing values should never silently go missing. It's not obvious when you run the plot that the values are missing, but you'll see that R does throw an error when that happens. So here's your plot. You don't see any issues with it. Looks good. However, there are 9 missing rows, and you can see that right here. So it'll tell you that you have 9 missing rows. So you can suppress that by using the geom point, the na.rm equals true. So if you run that, you'll have your scatter plot and you won't get an error. So we can go back and take a look at the scatter plot. Looks the same. So that's one way to filter out and deal with outliers. Now we're going to move on to covariation. We talked about variation, which describes the behavior within a variable. Covariation describes the behavior between variables. Covariation is the tendency for the values of 2 or more variables to vary together in a related way. The best way to spot covariation is to visualize a relationship between 2 or more variables. How you do that should depend again on the type of variables involved. A categorical and continuous variable. It's common to want to explore the distribution of a continuous variable broken down by a categorical variable. As in the previous frequency of the diamonds dataset. The default appearance of the geom poly, which we'll look at soon, is not that useful for this sort of comparison because the height is given by the count. That means that if one of the groups is much smaller than the others, it's hard to see the difference in shape. For example, let's explore how the price of diamonds varies with quality. So here's the code for that. We can run that and it will plot it away in the quartz 2. We look here, this says that ideal diamonds have the highest count and they look like they have the highest price, which makes sense. That's reasonable. And then you can see the very good and premium are second, and then you have good third, and then fair at the very bottom. That seems pretty reasonable. However, you have to keep in mind that this doesn't take into account the number of counts for each type of diamond. It's hard to see the distribution. It's hard to see this because of this right here. So you can see there are way more ideal diamonds than there are fair or good diamonds. So we'll go back to R and see how can we deal with that. To make the comparison easier, we need to swap what is displayed on the y-axis. Instead of displaying the count, we'll display the density, which is the count standardized so that the area under each frequency polygon is 1. So we can run that next piece of code right here. And when we do that, what we'll see is very interesting. Basically, this normalizes each type, not qualitative, for each type of diamond, so for each categorical variable, it normalizes the distribution. So now we can see that ideal diamonds, really, they cost the most. I mean, that's very surprising. And you weren't able to see this in the last plot because the frequency was hard to see. So another alternative to display the distribution of a continuous variable broken down by the categorical variable is a box plot. A box plot is a type of visual shorthand for a distribution of values that is popular among statisticians. So let's take a look at the box plots we have drawn up here. The box plots, so the box stretches from the 25th percentile of the distribution to the 75th percentile of the distribution for that category. So this is a distance known as the interquartile range, so the IQR. In the middle of the box is a line that displays the median. So that's the 50th percent of the distribution. These three lines give you a sense of the spread of the distribution and whether or not the distribution is symmetric around the median or skewed on one side or the other. Visual points that display observations that fall more than 1.5 times the value of the IQR from the either edge of the box plot. These outlying points are unusual, so they are plotted individually. So you can see all the dots you see, are outliers that are more than 1.5 times the IQR. So remember the IQR is this value range right here. So if you double it, it'd be right here. If you take 50% of that, it'd be right here. So then 1.5 times more than this are all outliers, and those are their individual points for those. A line or whisker that extends from each end of the box and goes to the furthest non-outlier point is the distribution. So you can see the whiskers. So these are the whiskers, the line. So there could be a few points within this line, or there could be thousands. We don't know, we can't tell, and that's by design because it's just a whisker. So this shows you a good way to look at the distribution and see again that fair diamonds are the highest priced diamonds amongst all the diamonds that we have available in this data set. So we reviewed box plots, covariation, and outliers. Now you should have a good understanding of how to really start your data analysis and do some basic data discovery with your data sets.